Okay, so in this video, we're going to do a little activity that looks at the graphs of sines and cosines. We're going to do this activity in class, but now I'm going to do it for you and you just get to watch. You can also get on Desmos if you'd like and share and take a look at, kind of follow along with what I'm doing. Okay, so hopefully right now on your screen, you see my video, and then you also see Desmos, our free graphing utility. We've got a unit circle over here. And then we also have some words down here, just some reminders. So what we want to do today is we want to take kind of our unit circle and we want to translate the unit circle into graphs of the sine function and the cosine function. So the really important thing to remember when we start is remember that that unit circle has radius 1. Okay, and so if we're thinking about the unit circle and we're thinking about cosine and sine, remember that cosine of theta is x over r in terms of our right triangle. If our radius is 1, that means x over 1 or just x. So as we're starting to graph the cosine function, and that's what we're going to start with, cosine, we can just think of cosine of theta as being equal to the different x values from our unit circle. Okay, so when we're graphing cosine, the cosine function, what we're really graphing is we're graphing ordered pairs that look like theta, an angle, and then the value of cosine. So we're graphing things that look like theta, oops, and the value of cosine theta. So we're going to plot a bunch of ordered pairs that are in this form, theta, the cosine of theta, and then we're going to look at what function that actually makes. Okay, so using our unit circle, our first value of theta here is 0. So our first point is going to be 0, and then remember we're taking the x values 1. So when theta is 0, our cosine has value 1. And notice that that went up here on our little graph here. All right, the next kind of common value that we have is pi over 6. I'm going to work with radians today. So next we have pi over 6. That's our theta value. When theta is pi over 6, our cosine is equal to the square root of 3 divided by 2. So there's our next little point there. Next, up here, right, our next theta value is pi over 4. Whoops. And at pi over 4, our cosine is equal to this x value, the square root of 2, divided by 2. Moving along, next is pi over 3. At pi over 3, the cosine is equal to 1/2. Oh my goodness. And then let's finish out this first quadrant at pi over 2. What's the value of cosine? The value of cosine at pi over 2 is 0. Oops, gosh. Okay, oh my goodness. Okay, so now we've got a whole selection of plots for our graph here, but let's go ahead and make this a little bit bigger. So I'm going to zoom in a little bit. Okay. And so I'm kind of using some of my prior knowledge here, but that's okay. Okay, all right, so here's the points that we've plotted. They kind of look like this. Hold on just. All right, how to make a paper airplane there for a 5-year-old. Okay, so here's our points in the first quadrant. Now let's continue on to the next quadrant. So here, our next value for theta is 2 pi over 3. At 2 pi over 3, our cosine is equal to negative 1/2. Moving on, next we have 3 pi over 4. So our theta is 3 pi over 4, and our cosine value is negative square root of 2 over, oops, over 2. Okay. Next we have 5 pi over 4 for theta. And at 5 pi over 4, the value of cosine is negative square root of 3 over 2. And then finishing out that second quadrant, we have, when theta is pi, cosine is equal to negative 1. Okay, so here, take a look at what's happening, oops, with our made a mistake. I'm looking at this and I'm thinking that point shouldn't be there. That's because 5 pi over 6, I put in as 5 pi over 4, my bad. There we go. Now we're starting to get the graph of that cosine function. So I'm going to pause the video for a minute, and then I'm going to finish putting in the points. I'm going to finish putting in all the rest of the points for the remainder of our unit circle, and then we'll come back together and see what we. Okay, so on our graph, I've now put in the rest of the dots here. So I'm going to move our window a little bit. And now look, we can see this is starting to make a shape here. Okay. Now, remember that we can go around the unit circle more than once. So I've put in all of everything here, but we could continue this. And if we continue this, this pattern is going to continue, right? So we would just basically take this and repeat it one kind of set of things over. So I'm going to go ahead and show you what I mean by that. So I'm going to pause again. Okay, so I put in the next couple dots here. So here was our 2 pi over 1. That's when we get back to our starting spot on the unit circle. And then if I want to go all the way around and get here again, so imagine we're going all the way around, so 1 full 2 pi, and then we're going a little bit further, pi over 6. That would be 2 pi plus pi over 6. This would be 12 pi over 6 plus pi over 6, or 13 pi over 6. At 13 pi over 6, right, which is the same thing as 390 degrees, we would be here again, and so our cosine would be equal to the square root of 3 over 2. So that's this dot right here. Notice that we're just starting to repeat the pattern that we already had. So I went ahead and put in the next kind of set for going around one full time and re-entering the first quadrant. And notice that we're getting that repetitive pattern there. So we can start to see our cosine graph here. And because this graph repeats, this is called a periodic graph. So the graph of the cosine function is a periodic graph, meaning it repeats the same pattern over and over and over again. So now that we have these plotted points here and we can start to see what our cosine graph looks like, hopefully we can see where those values are coming from. Let's go ahead and have Desmos actually graph the cosine function. Okay, so here we go. Look, that perfectly matches those points that we've put in. Now notice that periodicity that we were talking about. This function is periodic, meaning it repeats, right? So this x equals, so from 0 to 2 pi represents one period of this graph. And if we zoom out, we can see that this shape, this pattern, is just repeated over and over and over again. So our cosine function has a period of 2 pi, meaning it repeats every 2 pi kind of little units there. The other things that we can look at as we're looking at our cosine function, right, is we can see that it starts up here when theta is 0, right? Our cosine function is equal to 1, so it starts up here and then creates those nice little cosine waves here. We call this a wave function or this periodic function, okay? Now, let's go ahead and do the same thing for the sine function. So I'm going to pause the recording, kind of clear our graph, and then we're going to kind of graph the sine function. What do you think it's going to look like? Will it be similar to the cosine function? All right, so now let's try and do something similar with the sine function. So remember that when we're working with the unit circle, our sine function, sine of theta, is equal to y over r, thinking about our reference triangle. If we're working on the unit circle, our r is equal to 1, so we really have y over 1, which is just y. So we're going to use this, that sine of theta is equal to y, and we're going to be plotting things that look like theta, comma sine of theta. That's going to be our ordered pair, our xy value for our graph of the sine function. So again, let's go ahead and start at 0. Well, when theta is 0, our sine is equal to 0. So there's our first point. Next, we'll go up here to pi over 6. When theta is pi over 6, what's our sine function equal to? It's equal to this x value, 1/2. Next, we'll look at when theta is pi over 4. When theta is pi over 4, our sine is the square root of 2 over 2. And next we'll look at pi when theta is pi over 3. When theta is pi over 3, our sine function is equal to the square root of 3 divided by 2. And finishing this guy out, finish this first quadrant out. When theta is equal to pi over 2, our sine function is equal to 1. So there's the points from those first values in our quadrant 1. So again, I'm going to pause the recording, put in the rest of the points for the rest of the unit circle, and we're going to kind of get a picture of what our sine function looks like. Okay, so now I've plotted the rest of the points from our unit circle. You can see them here, right? So we had stopped, let's see, we had stopped here at the first quadrant, and so I've just put in the rest of them where theta is our first part of our ordered pair, and our second part is the value of sine at that value of theta. And notice that we get this nice kind of periodic wave shape, just like we saw for cosine. It just looks like it's a little bit different. It still has a period of 0 to 2 pi. Now, just like the cosine function, right, it has that period of 2 pi, so it's going to repeat every 2 pi. And we could put in more points here, just like we did with the cosine function, but I think at this point, let's just go ahead and put in the actual graph. So here's our graph of the sine function. We can see that periodic nature, or this repeats or has that same pattern every 2 pi units. And again, it makes that nice periodic wave function. So what I'd like to do now is let's go ahead and look at both our sine and our cosine function together. So there's our sine function in black and our cosine function in green. I might go ahead and take the points off so it's a little easier to see. Now, what do we notice about these functions? Well, they look really, really similar, just slightly offset, right? In other words, they kind of make the same shape. They have the same periodic nature. They each repeat every 2 pi units, but they're just slightly offset from each other. And that actually makes a lot of sense when we remember that these two are co-functions. So remember we saw that co-function relationship where they're just kind of differ by 90 degrees or by pi over 2 degrees. So if you could imagine picking up this green function, our cosine function, and moving it pi over 2 units to the right, it would actually be sitting right on that black sine function there. And I can actually do that with my graph here. So notice if I move our cosine function 2 units to the left, it's sitting right on top of our sine function there. Now this is involving some horizontal shifting of functions, and we'll talk about that a little bit more. But it's kind of interesting to see the periodic nature and the fact that these two are really closely related. Now some other things to pay attention to. We've talked about the fact that these have a period of 2 pi, meaning they repeat every 2 pi. The other thing that's interesting is notice that these don't go above 1 and below -1, kind of on our vertical axis. So this is what's known as the amplitude. Amplitude has to do with, if you're thinking of waves, the height of the wave. So these guys go between -1 and 1, and that is their amplitude. Now again, we're going to be able to change that amplitude if we change the function. But their base amplitude is -1 to 1. Notice that that also tells us something about the domain and range of these functions. I'm going to turn off sine for a minute so we can just look at cosine. So this is the graph of our cosine function. Okay. Now, domain is the x values, and notice that this is going to take on all of the x values. Okay. So our domain is going to be -infinity to infinity. Our range, however, is not going to be everything. Our range has to do with the y values or the vertical values. And notice that for our basic untransformed cosine function, this only goes between -1 and 1. So the range of our cosine function is -1 to 1. The same thing is true for our sine function. Our sine function has domain -infinity to infinity, but it has range -1 to 1. All right, the last thing that I want to talk about in this first video is I want to talk about even and odd functions. I apologize. So again, we've got the cosine function up there in green, the sine function up there in black, okay? So whether a function is even or odd has to do with its symmetry. Okay, so what is symmetry? Well, there are 2 main types of symmetry. The first, well, there's more than 2, but for us, there's 2 main types of symmetry. The first is line symmetry. So line symmetry says something is going to be the same when we fold it in half, okay? So line symmetry, also known as mirror symmetry, if we look at our cosine function, so I've just taken the cosine function off, it's actually symmetrical about one of the axes. So this is our y-axis and this is our x-axis. Which one is our cosine function symmetrical on? Well, it's symmetrical about the y-axis, right? In other words, if I folded my graph in half on that purple line, the two halves of my cosine function would match up. So our cosine function has y-axis symmetry, which means that it is an even function. So being symmetrical about the y-axis is an even function, okay? Now let's think about our sine function. Well, our sine function does not have y-axis symmetry because clearly if I fold it in half along that purple line, the two halves of that line would not match up. It also does not have x-axis symmetry. So x-axis symmetry would be if I folded in half along the x-axis, the two halves of my function would match up. So what kind of symmetry does our sine function have? Well, it doesn't have line symmetry. It turns out it has something known as rotational symmetry. Okay, so what I want you to imagine, and I'm going to actually have a little picture here that I'm going to show you. Okay, as always, if you can be patient with my drawing capabilities, but here's a sketch of the sine function. Now, rotational symmetry says if I rotate this, before I get all the way back to where I started with, my graph will look the same. And in fact, it seems like when I rotate it halfway, so notice that this is now upside down, this looks exactly the same as where I started. So this has rotational symmetry about the origin. In other words, if I put a pin in the origin and spin my function around the origin, right, it's going to look the same. So our sine function has origin symmetry. When a function has origin symmetry, we say that it is odd. So our sine function is an odd function. Our cosine function is an even function. We're going to use that terminology as we move on.